today is the electrical activity of the heart. We talked about the heart on Friday. We introduced the structure of the heart. We talked about the valves, right? We talked about how the ventricles contract to empty blood into those major vessels, and the atria contract to fill the ventricles, right? Empty the blood from the atria down into the ventricles. Today we're going to talk about the electrical basis upon which that is possible, right? What are the ions that are moving? What's happening inside a cardiac cell to bring about that contraction? And you'll see a lot of similarities, right? I'm going to continually point them out between cardiac muscle, skeletal muscle, and smooth muscle in terms of that electrical activity and the structure of itself. Right? So first of all, the heart has what we call autorhythmicity. Autorhythmicity. And that means that the heart can generate its own action potential, the cardiac cell, certain cells in the heart. Okay, and we talked about this phenomenon before, that pacemaker ability of the heart, where in the absence of any external stimuli, the heart would generate an action potential. Right? We're going to talk about what those cells are. So they're going to be responsible for setting the heartbeat or setting the rhythm of the heart. Just by nature of initiating those action potentials, they're going to control how fast the heart is beating, how slow the heart is beating, and the rhythm of the heartbeat. So the two autorhythmic cells are the pacemaker cells and the conduction fibers, right? The pacemaker cells and the conduction fibers. The pacemaker cells are going to initiate that action potential. This is where the action potential starts or is generated from. So we're going to talk about what those two cells are. The conduction fibers simply propagate that action potential throughout the muscle tissue. All right, so the pacemaker is going to initiate the action potential. The conduction fibers, which are different types, we're going to get to them, they are going to propagate or send or transmit that action potential throughout the muscle tissue. Right? Now, these cells generate very little force, if any at all. So they're not going to be the main contributors in terms of contractile force. Right? The remaining cells outside of these two types of cells are the contractile cells of the heart. They are going to contract and generate the contractile force of the heart that allows the heart to contract. Okay? Now, as you mentioned before, the pacemaker cells sets the rhythm or the tone of the heart, and they do so by initiating that action potential. That is their unique function. All right, we're going to talk about what those two are, and then the conduction fibers rapidly propagate or generate that signal. Now, the two pacemaker cells are called the SA node and the AV node. The SA node and the AV node. Right? So the SA node, also called the sinoatrial node, is at the top of the atria, the top of the right atrium, right? And it's going to sit there, and it's a cluster of those pacemaker cells that we talk about, and they are rapidly firing out action potentials. This is going to be the fastest rate of action potential generation, action potential initiation here. And so the SA nodal cells are going to fire their action potential. Some of the conduction fiber cells are going to take it to the second pacemaker cell, which is the AV node, also called the atrioventricular nodal cells. Right? The AV node or the atrioventricular node. Right? So those two types of cells, or those two areas in the heart, is a condensation of two types of pacemaker cells. Okay? The conduction fibers, there are three types. There's the internodal pathway, and these are the fibers in the heart that transmit that impulse from the SA node to the AV node. Hence, they're called internodal. Right? They're going to take the impulse from the SA node and give it to the AV node. That's why they're called internodal, in between those two nodal cells, or groups of cells. Then there's the bundle of His. Right? The bundle of His is also called the atrioventricular bundle, or the AV bundle. Right? So you may hear me say those terms interchangeably. And that is going to propagate that signal from the AV node. Right? That's where we left off, from the AV node down into the ventricles. I'm going to draw this out and talk more about it, but I just want you to know what these fibers do. Finally, the Purkinje fibers is going to propagate that signal throughout the ventricle. So the atria, right, to the SA node, to the AV node, to the bundle of His, to the Purkinje fibers. All right, let's talk about the speed of this conduction here. So the action potentials being fired from the SA node is going to be the fastest rate, right? About 70 to 80 action potentials per minute. Hence, right? Hence, this area is the heart, is the generator of the heartbeat, the pacemaker. Because they're firing action potentials, right? The SA node cells are firing action potentials so rapidly, they are going to set the tone of the heart. They're going to set the heartbeat or the pace of the heart, which is the pace, which is why they're called the pacemaker cells. The AV nodal cells are firing action potentials at a slightly slower rate, right? 40 to 60 action potentials per minute. And so there's a slight delay in the impulse from the SA node to the AV node. And we're going to talk about why that delay is very important. And then the bundle of His and the Purkinje fibers are firing significantly slower at about 20 to 40 action potentials per minute. Okay? Now, cardiac cells are going to be linked together by gap junctions. This is a phenomenon that we talked about before. And this is going to be very important in maintaining the electrical coupling of the heart. When we say electrical coupling, we mean that all the cardiac cells have the same information. Right? What's happening in my cell is happening in that cell, and so on and so forth. So they are sharing information through those gap junctions. Remember, we said gap junctions were those tiny channels in between two cells where they sort of spoke to each other, communicate, exchange information. Right? Now, right here. Okay, let's talk about some of the structures of the cardiac cells and how this impulse is really translated in terms of the function of the heart. So because the impulse is generated in the SA node and then transferred to the AV node, right, it's also going to propagate through both of the atria. So going to start in the right atria, propagate throughout both atria, and then it's going to be delayed as it gets to the AV node. As a result, both atria are going to contract fully before the signal even gets to the ventricles. All right, I'll say that again. The signal or the impulse, or those action potentials being fired, is going to start in the SA node, right? It's going to be propagated throughout both the left and the right atrium. And then there's going to be a slight delay before it actually hits the AV node. This delay is going to be important in allowing both atrium or both atria to contract before the signal gets to the ventricles. Okay? When the signal gets to the AV node, it'll then go to the bundle of His, then out to the Purkinje fibers. And as a result, both atria contract, followed by both ventricles contracting. So the atria contract fully, then the ventricles contract. And that is the importance of that delay, that slowing down of the AV node, to sort of hold off that impulse so that both the atria can contract and then the ventricles contract. And if you remembered how blood flows to the heart, we'll see why this is important, right? The atria have to squeeze their blood into the ventricle. So you can't have all four chambers contracting at the same time. Right? The atria have to contract fully, squeezing their blood into the ventricles, and then the ventricles contract fully, squeezing their blood out. Okay, and that's the importance of that delay. Now, as we mentioned before, the communication one cell to the other, right, the propagation of that impulse to the conductive cell, to the contractile cells, happens via gap junctions. Now, there are some structures within the muscle cells, right? In between two muscle cells, that area is called an intercalated disc. And it's called an intercalated disc because there are several, because of the way it appears on histological staining. So when you look at this under the microscope, it's sort of a wavy little disc, which is the joining point between two cardiac cells. And the two important structures that are found at this junction are desmosomes and gap junctions. Okay, so I'll say that again. The intercalated disc is the area where two adjacent cardiac cells are sitting next to each other, right? That junction in between them is called the intercalated disc, and there are two important structures found here, the desmosome and the gap junction. We talked about the desmosome already, right? And can anyone remember what the desmosome does? What was the function of the desmosome? Good, thank you. So it's going to hold the cells together. Remember, you said it sort of zipped up the two sides of those cells. There was an anchoring junction that kept both cells very nicely held together. So that's going to be very important in cardiac cells because of the continuous contraction and relaxation, right? Filling and emptying of the heart. The mechanical stress, that continuous stretching of the heart can put some wear and tear on those cells. So having them very nicely anchored together is going to be very important to withstand that mechanical stress. All right, so this is what the SA, on the left, what we're seeing is the SA node and the conduction of the SA nodal impulse throughout the contractile cells of the heart. So in red is going to be the pacemaker cells of the SA node, whereas what we're seeing here is the actual contractile cells of the heart. And we can see that the action potential is being propagated through each cell via this little squiggly line. So this is the intercalated disc. And the impulse is going to pass through that area to get to the other cell. Now on the right, we're seeing a much bigger version of this communication here. So this is one cell, this is another cell. This area is called the intercalated disc, right? This is the desmosome that's sort of zipping up the two sides of those cells, keeping them nicely anchored together. And this is the gap junction where the communication can pass from one cell into the other cell. Okay, so each cell does not have to be excited. That impulse is going to pass from the SA nodal cells to one contractile cell, to another contractile cell, and so on and so on and so on. Okay, now I just want to point out here that within the muscle cells of the heart, we also have the sarcomeres, right? And just to remind you, the sarcomeres is what gives the muscle its striated appearance. It's going to be found in skeletal muscle, it's going to be found in cardiac muscle. Okay, so this arrangement of the thin and thick filament is called a sarcomere.